Okay, let's have a look at this example. And I'm going to do lots of stopping the video throughout this and write the solution up just to reduce the time on the video. Okay, in this example, it's looking at the rate of increase in a population of green and purple flying bugs. Would have been more interesting if they were yellow flying bugs, anyway, found at Ashfield is proportional to the excess of the population over 200. So here is the indicator that we've got a constant, D, and we're comparing the rate of change to this value, 2000. That is, dp/dt is your constant p minus 2000 for some constant k. Initially the population was 3,000. 3 weeks later it reached 8,000. So you probably want to, in reality, read that a couple of times. You know that you're going to substitute initially t equals 0. And the population, and yes, they're using P, was 3,000. 3 weeks later, so that'll be T is equal to 3, and we've set our unit of time to be weeks. The population is 8,000. A showed that this equation satisfies the differential equation where A is a constant. So like I said in the introduction, this is very common, and really you came across similar questions in the advanced exponential growth and decay questions. However, I'm going to show you a couple of options, and I'll obviously talk about those because we need to do something a little bit different to what you previously did. So this show that this equation satisfies the differential is a little bit different to previously. I'll just stop the video now and fill it out. You can see there I haven't done very much of the solution yet, but I do want to talk about where we are at the moment. So clearly you write your equation and you know to differentiate both sides of the equation. And when we differentiate this, 2000 disappears, we get k times ae to the kt. Now, that is not looking very much like where we're heading, which is up here. So we've got k times ae to the kt. Now, solution 1 can be that we introduce this different little technique, and it's nothing more than I'm going to introduce, hang on, there should be a k out the front. I'm going to take k out, and you know what that would be, we'd have an ae to the kt sitting there, but I'm going to introduce, add a 2000 in and subtract the 2000. So what are the two main things that have happened here? I've taken the k out totally of ae to the kt, added in 2000 but subtracted 2000. Now, you may be able to see why I did that. We've got k outside of this part inside the bracket. 2000 plus ae to the kt is just p. And so we get p minus 2000 in the bracket as a solution to, which looks like our differential equation. Now, I'm going to just show you another method that we could show that this equation here actually satisfies the derivative. And again, I'll pause the video. So a second method is to obviously start with P equals 2000 plus AE to the KT and differentiate both sides, so nothing different to here. But if I call that 1, then I'm going to say from 1, AE to the KT is equal to P minus 2000. And let's call that 2. And then we can simply sub 2. Maybe I'll have to go back and call this one 3. Sub 2 into 3. That is dp dt is equal to k times P minus 2000, because we've got a second expression for AE to the KT. So there's your two methods. Either one is correct. So you can see to find the values of A and K, we start with our solution equation, and we know that when T is 0, population was 3,000, and when T was 3, the population was 8,000. So we can substitute those straight in, which is similar to what you did previously. And those of you who are thinking, is this really, do we have to do it this way? Then I'll come to that in a minute, because no, you don't have to do this way. However, if you do just put your values in, 3,000, formula 2,000 plus A times 0, then you'll get that, subtract the 2,000, that goes to A. So you'll get A is equal to 1,000. But those of you who have learnt this, that A in this format is equal to P minus D at time is 0. Now this only happens at time is 0. Then we will have that A will be 3,000 minus the 2,000, which is actually equal to 1,000. So you can get your value of A using that formula. Once you've got that, you sub it in, which you would have done previously. So P is equal to 2,000 plus 1,000, E to the KT, and then you solve for K. So we use our other piece of information, subbing T equal to 3, P equal to 8,000, and you can see that we're going to require logs because we're finding an index. Okay, there you can see the full solution now for finding A and K, and nothing new. We've got subbed our second piece of information. When T is equal to 3, P was 800, and we get 6,000 on 1,000 is e to the 3k, and taking logs of both sides, then we get k is log 6 on 3, and p is, sorry this is so small, scrunched up, that should be 2,000 plus 1,000 e to the log 6 on 3 times t. Okay, so, and as you would expect from there, we just use that equation now to answer some other questions. So find the population, find P when T is equal to 7, correct to the nearest 10 bugs. So again, I'm going to pause the video and write out that solution. So it's a very simple substitution. For T is equal to 7, and then it just becomes a calculator question. I did actually bracket all of that when I was using my calculator, and it just depends, I guess, on how proficient you are with using your calculator, whether you managed that exponential calculation correctly or not. The question did say to the nearest 10 bugs, please always show your full calculated answer, then do the appropriate rounding. Now, part D, find when the population. So this one will be find T. When P is 500,000. So again, you can expect that we'll be using some logs, but again, I'll pause it and write up the solution. So there you can see that I've rewritten the equation, subbed in the 500,000, solved this equation, brought the 2,000 across, divided by 1,000. So that calculation there ends up 498. Take the log of that, gives me the power, which is log 6 on 3 times t, multiply by 3, divide by the 6, log 6, to give t, and be careful doing that calculation. The question required it to the nearest 0.1 of a week, and so we get 10.4 weeks. So that completes that example.